Okay, so today we're going to look at the formalization of finite horizon deterministic dynamic programming problem. First of all, it's finite horizon because you will be starting at some state and then you exactly have n states, right? You'll be applying n controls and you will go to state xn where it terminates, correct? So that's why it's finite horizon. In an infinite horizon problem, you'll stay at x0 and essentially you will never end, right? This xn would not exist. And it's deterministic because there is no stochasticity in this problem, as I'll explain. And it's a dynamic programming problem. So the setup is as follows. You start at some state x0 and you will be applying a set of controls. For example, I am at state xk and I apply the control uk. This is called the control, right? In more AI community, this could be called an action that is taken or control that is applied. Now, once a control is applied, the state changes from xk to xk plus 1, right? And it is deterministic, right? So the control equation is given by xk plus 1 is equal to f of k given a state xk and then uk. This control equation will determine what is the next state, xk plus 1, and this is deterministic, right? There is no stochastic term here. There is no wk, that will be the stochastic term. Since there is no stochastic term, it is a deterministic equation. So the terminology is xk is called the state of the system and uk is the control, and the state of the system must belong to the state space sk and the control must belong to the control space, right? And the control space is different at different states. So this is given by this equation. This is called the control constraint, right? So uk belongs to capital uk xk, so it depends on the state xk. Given a state xk, there are only few set of controls you can apply. An example of this could be, suppose I don't know, this is a different problem, but let's say you are solving a grid problem and your agent is here, right? Given the state xk, you can only go either down or to your left or to your right, but you can't go up, right? So this control of going up cannot be applied in this state, correct? So that is the control. And along with this transition going from xk to xk plus 1, you also have a cost function, right? This cost function is also dependent on the k, the stage, and given a state xk, uk, this cost function will tell you what is the cost of this transition, correct? So now, given this setup, right, wherein you have x0, you are going to xn. Also, I forgot to mention there's a terminal cost. Given that you reach a terminal, there is a terminal cost gn of xn for the terminal state, correct? So, okay, let's move on. So now, given initial state x0 and a set of controls u0, u1 to un minus 1, you can get the total cost of this control sequence, right? Given a state x0, u so on, u0 to un minus 1. The total cost of this control sequence is the terminal cost plus the cost at each stage, right? This is a pretty simple equation. Now remember that I could also have written this equation j of x0, x1, so on, xn, correct? But these are equivalent, right? Because given a control sequence of u0 to un minus 1, I can always deterministically determine x1 to xn minus xn, correct? Because of the deterministic nature of the control equation, xk plus 1 is equal to f of k xk uk, correct? So this is equal to this. So this is the total cost of the control sequence, u0 to un minus 1. Now what is the problem we want to solve, right? We want to get to the optimal cost, correct? This is the optimal cost. Optimal cost is denoted by j star of x0. So given an initial state, what I want is this function j star, that is the optimal cost function, that minimizes over all the control sequences that are possible, right? So all the control sequences that are possible must follow the control constraints. Now, among all the control sequences that are possible, this is the cost. I just want to minimize it, correct? So this is the problem of finite horizon deterministic dynamic programming problem, right? Now, okay, this is the setup, that's great. Now let's see how can we solve this, right? We obviously want to solve this problem. Now, one way to visualize this, in case the state and control spaces are finite, right? In many of the problems, the state and control sequences are finite, right? This could be the problem of traveling salesman, right? Traveling salesman is an example of when the state and control sequence spaces are finite. In that case, one could visualize this problem in the form of a graph, right? So this graph is set of states, the nodes are the states, and any edge represents the transition from one of the initial state to the next state, and each edge can have the cost as the length of the node, length of the edge, correct? So then we can have a artificial terminal node that is added to all these terminal nodes. We add a terminal node, and this terminal costs can be the length of these arcs, correct? So this is a very simple graph problem, and the problem of solving J star, right, which is the optimal cost of going from x0 to the terminal node terminal node t. This is a very well studied problem. That is the problem of shortest path problem, right? We are given a standard graph. You are given maybe a source node x0. You want to go to the node t. You just want to find the shortest path, right? This is the shortest path problem. As I've said here, the point is we are interested in the optimal cost, but that's not everything we need, right? What we also need is this control sequence. u0 star to un minus 1 star. This control sequence is actually what we need, correct? So, all right. So this is equivalent to the shortest path problem, which is very well studied in the literature. So one can apply this shortest path problem given the computation and the states are finite in the sense that the computation is possible. If the states are infinitely large, then such a setup won't be possible. But let us dive deep into how do you solve this problem, right? So we want to solve this problem. Now, before we solve this problem, we have to understand a principle of optimality, right? Principle of optimality sounds like a big term, but what it ideally means, before I give the formal definition of principle of optimality, I would like to give an example. For example, you are trying to go from, let's say, this is India as a country, and then let's say you plan to reach Finland, right? This is Finland, and let's suppose there is Dubai between. Let's suppose the optimal path of going from India to Finland is, let's say you have some intermediate nodes and you go to Dubai, and then let's say you go to Finland, right? This is, let's suppose this is the optimal path, right? This is the optimal path, right? I have computed the optimal path. Now I ask you the question, what is the question I want to ask you is, what is the optimal path for going from Dubai to Finland, right? What is the optimal path? Obviously, intuitively, you can tell me that the optimal path is the same as this path, correct? The prior information is actually not so relevant in this question, but the optimal path of going from Dubai to Finland would just be the tail subproblem or the tail solution, right? So let's say you go from India to some country C1, so on and so forth, to Dubai, and then CK+1 to so on to Finland. So the optimal, if then this is the optimal path from India to Finland, then the optimal path from Dubai to Finland should just be the subproblem, correct? That is what is principle of optimality. we can look at this formally. So given that u0 star to u1 star to un minus 1 is the optimal control sequence with x0, then we can obviously get x1 star, x2 star, xn star using the system equation. The system equation again is xk plus 1 is equal to f of k xk uk, right? This is what is called the system equation, right? So using the system equation, I am already given the optimal control sequence u0 star, u1 star, un minus 1. Given this optimal control sequence, I can get this optimal states, correct? Now I want to consider the problem of starting at xk, and I want to minimize what is the cost to go, right? The cost to go is basically the cost to go from xk star to the terminal state, right? So you can write, this is how it is represented, jk of xk star. This is the cost to go from the kth stage and the state xk star, correct? Basically, I'm asking the question, I'm at Dubai, I want to go to the terminal state of Finland. What is the optimal cost to go, or what is the cost to go, right? So that is gk of xk star and apply the control uk plus gm, I mean, you just read this equation, sum of going from k plus 1 to n, g of m xm um plus terminal xn, correct? So this is for a control sequence, random control sequence uk, so to un minus 1, right? This is the control sequence here in this question. So obviously I want to minimize this over all the control sequences possible, right? And the principle of optimally says you don't have to solve this problem, since at the start of the problem I am already given this optimal control sequence. I just have to take the tail of this optimal control sequence, that is uk star to un minus 1 star, right? This is principle of optimality, correct? Now given this principle of optimality, you can actually come up with an algorithm to solve the problem. So the algorithm is very simple. What we want to do is we want to construct this set of functions, jn star xn, jn minus 1 star xn minus 1, and so on and so forth. So basically the algorithm involves the following, right? We want to construct the optimal cost to go starting from terminal state all the way to start, right? So let's look at this in more detail. So intuitively, I think you can come up to this sort of formulation here. I mean, one could as well prove it starting from the optimal cost function definition. You can come up to this, but I think this is very intuitive to understand, so I'm not trying to prove it here. The left hand side is optimal cost of the tail subproblem starting at state xk, right? So this is, I am starting at state xk. I want optimal cost to go, right? What is involved? It involves minimizing just the controls I can apply from xk. This is the control constraint. So I'm at state xk. So I'm at state xk, right? I can apply a set of controls. Let's suppose this is uk1, uk2, uk3, correct? And so corresponding to each of these transitions, so this, it would be f of fk xk uk1. This is fk xk uk2. This is the state, and so on and so forth, correct? So these are all the states. So this is the cost of this transition going from uk to xk, and apply the control uk. In this case, let's say uk1. Now what I'm saying, what this algorithm says is, from this I don't have to go further. I just want to add the sum, optimal sum from this state, right? So let's suppose I already have this optimal sum, then I can just add this arc to this optimal cost to go from the next state, and I just have to minimize over this set, right? and I will get this, right? Which is very intuitive to understand. Yeah, obviously one can mathematically prove this. The proof is in the book, but this is a very intuitive equation to come up to. Now, what we have is this function called jk star. This is called the optimal cost to go function. Basically, what it gives me is, maybe I'll explain it in this graph. Right. So suppose I have already let's suppose, yeah, this one. I have this function jk star, right? What it tells me is the input to this function is xk, right? And the output is optimal cost to go, right? This will give me a scalar output, that is the optimal cost to go from xk to terminal state, right? To terminal state, correct? So that is this function. It maps from all xk's, correct? The domain to this function is any xk in any stage, right? So once I have this such a function, right? This is basically a lookup table. I can look it up on any stage, any state at any stage xk, right? And it will give me optimal cost to go. So for example, I can say, hey, I'll take this state, right? And I'll put it in this function, and I'll get the optimal cost to go from here to the terminal state. I can do the same from here. At the same time, I can do that from here, which is x0. I'll get the optimal cost to go from this initial state, correct? So using the dynamic programming algorithm, I have computed all of this, right? I'll be illustrating this algorithm using traveling salesman problem in the next video, but I hope you're understanding what I'm saying. Now, let's see. So, okay. Now the question is, obviously getting this jk star is not what I want, right? This optimal cost to go is great, but that's not what I want. What I want is this control sequence, optimal control sequence u0 star to un minus 1 star, right? How do you construct this, right? The construction is pretty simple, right? We start with the initial state x0, right? And then try to minimize this, right? Just as you did before, but then you get the argument, right? So for example, you are in state x0, and you can apply all the controls, u1, let's say u2, u3, so on and so forth, and then you get the arc cost, or the cost of this edge, which is this, and then the optimal cost to go from this state, right, to a terminal state. And then you just keep doing this for all the controls possible, right? And then just take that control which minimizes this. Using this control, you can go to the next state, which is the x1 star here. This is the control equation, go to the next state, and keep repeating this process essentially, right? From here, you can again take all the controls possible, and then minimize an equation like this, you'll get it, right? So this is how you can, this is called online play, correct? This is online play, because you have this optimal cost to goes, and you're just trying to play online to get the optimal control sequence, correct? So yeah. So in this video, just to summarize, what we did was we have defined what is a finite and deterministic, right? Excuse the spelling, finite deterministic dynamic programming problem, right? And we have determined, we have introduced all the terms, right? And I have said, in addition to finite deterministic problem, if you add the condition that its state space is finite, right? State space is finite horizon, I forgot, finite horizon, right? So this is the finite horizon because there are exactly n stages, right? This process does not go on forever. There's exactly n stages. That's why it's finite. Deterministic because the control sequence is deterministic completely, which is fk xk of uk. There is no stochasticity in this equation that gives an x state xk plus 1. right? And if you add the part wherein the state space, right, the state and control space are both finite spaces, it becomes equivalent to shortest path problem, right? We saw what is the principle of optimality, right? Principle of optimality, and I have explained that. And then we also saw the dynamic programming algorithm to solve this problem, wherein you compute the optimal cost to go function. Once you compute this, then you can do forward algorithm to get the optimal control sequence, right? Optimal control sequence. So this is just a formalization. In the next video, we'll try to solve the traveling salesman problem to kind of get this in real world. How do you actually apply this? All right.